Some pieces of iron forged centuries ago have been left exposed to the elements rain, frost, shifting loads over time, and still they refuse to fail in the way modern metal usually does. Not suddenly, not cleanly. That alone feels strange, because if you actually examined them, you might expect the opposite. The surface is coarse, inconsistent, almost crude. By modern standards, it looks flawed, even inferior, and yet it endures. In parts of Europe, there are wooden frameworks still held together by their original iron nails after 400, even 600 years. When those nails are removed, people often expect them to snap under pressure. But they give, slowly, as if something inside the metal is taking the strain, spreading it out instead of letting it concentrate. And that's where it starts to feel unusual. Because when you look inside this iron, it doesn't reveal a smooth, uniform structure like modern steel. Instead, there are streaks, long, thin threads woven through the material, almost like layers folded into each other. At first, these were dismissed as leftover debris, slag, trapped during forging, imperfections, things that should have been eliminated. But those imperfections tend to appear exactly where fractures would normally begin. And instead of weakening the metal, they seem to interfere with the break itself, slow it, deflect it, as if the crack loses its path, unable to move the way it normally would, which doesn't really fit what we know. Because in modern materials, once a crack starts, it travels quickly, straight through, no hesitation. This behaves differently. It absorbs, it redirects, it delays failure in a way that feels intentional. But that's the problem. There was no formal science behind it, no microscopes, no engineered formulas, just heat, repetition, and hands that learned over time. So what exactly was happening there? Were blacksmiths unknowingly shaping a structure that we later removed in pursuit of perfection? Or were they following a method they understood in a way we no longer recognize? Something never written down, only practiced until it worked. Because if those internal defects aren't defects at all, then it leads somewhere uncomfortable. What if the way we define better metal today is exactly what made it more fragile? And if that's the case, then this might only be the surface of it.
Here's where it starts to break logic even more, because if this structure really helps prevent cracks, then modern steel should have evolved to do the same thing, but it didn't. In fact, we did the opposite. We removed the very thing that might have been protecting the material. Modern steel is designed to be as uniform as possible. Clean, controlled, predictable. Every part of it behaves the same way under stress. And that sounds ideal until you realize what happens when something finally goes wrong. It doesn't bend much. It doesn't slow down. It fails all at once. A single crack can move through modern steel almost instantly, like tearing a piece of paper. No resistance, no redirection, just a clean, sudden break. And in critical structures, that kind of failure is dangerous precisely because it gives almost no warning. But those old pieces of wrought iron, they don't behave like that at all. There are documented cases where ancient iron bars and fasteners have been under constant load for centuries. Wood shifting, weight pressing down, temperature expanding and contracting, and instead of snapping, they slowly deform. They stretch. They adapt. Almost like the damage is being absorbed across the entire structure rather than concentrated in one point. Which leads to a strange contradiction. The material we consider more advanced fails faster in certain conditions than something made with fire and hammer hundreds of years ago. That shouldn't happen. And it gets worse, because When researchers tried to recreate traditional wrought iron using modern methods, they could match the chemical composition, but not the behavior. The recreated metal looked similar, tested similar in controlled environments, but under real stress over time, it didn't perform the same way. Something was missing. Not in the material itself, but in the process. Old blacksmiths didn't just shape iron, they worked it slowly, repeatedly heating, hammering, folding, stretching, each strike slightly changing the internal structure, aligning those slag fibers in ways that weren't perfectly uniform, but weren't random either. And here's the part no one can fully pin down. They weren't measuring anything. No thermometers, no precise controls, just color, sound, resistance under the hammer. Decisions made in real time, based on experience that was never written down, only practiced. So whatever this structure is, it wasn't engineered in the modern sense. It emerged, and maybe that's the uncomfortable part, because if strength came from something unpredictable, something slightly imperfect, then modern manufacturing didn't just improve metal, it standardized it. And in doing that, it may have removed the very behavior that made it resilient in the first place. So the question isn't just how this iron resists cracking. It's why we stopped making it that way without fully understanding what we lost. At some point, the focus quietly shifted, not from weak to strong, but from adaptable to predictable. And that change didn't just happen in the material, it happened in the way people worked. If you watch a traditional blacksmith, there's something unusual about the process. It's slow, repetitive, almost meditative. Heat, hammer, turn, repeat, not to reach perfection in one step, but to gradually shape something that responds to pressure over time. The material isn't forced into a final form, it's guided there. And that's a very different mindset, because today we assume knowledge lives in formulas, in measurements, in machines that guarantee the same result every time. But for most of history, it didn't. It lived in hands, in timing, in small adjustments that couldn't be written down, only felt. A blacksmith didn't need to explain why a piece of iron behaved a certain way. He only needed to recognize when it didn't feel right and correct it, which means the final structure of that iron, those internal fibers, those irregular patterns, weren't designed on paper. They were the result of thousands of tiny decisions made instinctively over and over again. And maybe that's why we struggle to recreate it. Because when modern systems try to copy the material, they isolate variables, they control temperature precisely, they standardize pressure, they eliminate variation. But in doing that, they also remove the subtle inconsistencies that may have created strength in the first place. It's possible that what we call imperfection was never random. It was shaped. Just not consciously, not analytically, more like a rhythm than a formula. You can still see traces of this in surviving tools. Old axes, hinges, even simple iron brackets that have been used for generations. They don't just survive, they age differently. Wear is spread out, damage accumulates slowly, unevenly, but without catastrophic failure. Almost as if the material expects stress and adapts to it, and that raises a deeper question. If ancient craftsmen didn't fully understand the science, but still created something more resilient in certain ways, then what exactly were they optimizing for? It wasn't efficiency, it wasn't speed. It might have been something harder to measure, something closer to longevity. And if that's true, then the difference isn't just in the metal. It's in what they valued when they made it. At some point, we stopped asking how long something could last and started asking how fast it could be made. And that shift quietly changed everything. Because when speed becomes the priority, variation becomes a problem, so we remove it, we control everything, we make materials cleaner, more uniform, easier to predict. And on paper, that looks like progress, it looks like improvement, it looks like we finally mastered the material, but materials don't live on paper. They live in the real world, where stress is uneven, where temperature shifts, where pressure builds slowly over time in ways no system can fully predict. And this is where the trade-off begins to show itself. Because those old pieces of wrought iron were never perfect, they weren't optimized for peak performance in a single moment, but they didn't collapse all at once either. They bent, they resisted, they absorbed damage gradually, almost like the failure was being stretched out instead of concentrated. While modern materials often do the opposite. They perform better, stronger, cleaner, right up until the exact moment they don't, and when they fail completely, instantly, without warning. Perfect systems break perfectly. And maybe that's the cost we don't usually talk about, because in gaining precision and efficiency in building systems that produce identical results every time, we may have quietly removed something less visible, but just as important, something that doesn't show up in controlled tests, something that only reveals itself over decades, under real conditions, under real pressure. Resilience, not strength, not hardness, not perfection, but the ability to endure imperfection over time. And maybe that's why this feels uncomfortable, because this isn't just about iron. It's about a shift in how we define value. We replaced durability with consistency, longevity with speed, adaptability with control. And now, when we look back at something as simple as medieval iron, it doesn't prove we were wrong, but it does raise a question that doesn't go away easily. If something made with less knowledge could last longer, then what exactly did we improve, and what did we leave behind without even noticing?